All right, welcome back. So today we are diving deep. We're talking about the actual blueprint of the living world. We're going to peel back the layers and figure out what really makes an ecosystem tick.
Okay, so here's our game plan for today. First, we're going to tackle the big one. What even is an ecosystem? Then, we'll break it down into its parts, the non-living stage and the living actors on that stage. After that, we'll see how they all interact in this great interplay of life. And finally, we'll get into the actual rules of survival that govern the whole shebang.
First up, let's get our definitions straight. Think of this as a backstage tour of the living world. We're going to get the lay of the land before we meet all the individual performers. It sounds like such a simple question, doesn't it? What makes a forest? Well, a forest, or a pond. A pond? But the answer? That's where we get to the absolute heart of ecology. What is it that really defines these places? And here's the kicker. The most important thing to get is this. An ecosystem isn't just a bucket of animals and plants. It's not just a location. It's all about the interplay. It's this constant, dynamic web of connections, this active relationship between the living things and their non-living environment. It's all about interaction. Okay, so now that we have the big picture, let's start taking it apart piece by piece. We're going to start with the foundation, the stage itself. We're talking about the non-living, or what we call the abiotic components, that set the scene for all the drama of life.
And I absolutely love this way of thinking about it. The abiotic factors, things like rocks, water, sunlight, they're not just background scenery. No way. They are the stage, they're the lighting, they're the set design. They dictate what kind of play can even happen in the first place. So we can actually break this stage down into three big categories. First, you've got your atmospheric stuff. Light, temperature, humidity, you get the idea. Then you have edaphic factors, which is just a fancy word for everything to do with the soil. Its pH, what minerals are in it, its texture. And finally, topographic factors. This is just the physical shape of the land itself. Think of a steep mountain slope versus a flat valley. Each one creates its own unique little world. And this is such a great example of how just one of those factors can be a total gatekeeper. So if an organism is eurythermal, eury meaning wide, it can handle a big range of temperatures. Think of a raccoon, they're everywhere. But a stenothermal organism, steno meaning narrow, has this tiny comfort zone. A coral reef fish is a perfect example. The stage itself is literally deciding who gets to be in the play.
All right, the stage is set. So now let's bring on the performers. It's time to meet the living actors, the biotic components, and see what roles they play in this whole drama. So, in pretty much any ecosystem you look at, the whole cast of characters is defined by the flow of energy. It all kicks off with the producers, right? The plants grabbing energy from the sun. Then they get eaten by the consumers. And when anything dies, producer or consumer, the decomposers move in. They're like nature's ultimate cleanup and recycling crew, breaking everything down. Okay, now get this. This number tells a really surprising story. Every time energy moves up one of those levels, say from a plant to the rabbit that eats it, only about 10% of the energy actually makes it. 10%! The other 90% is basically lost, mostly as heat. And that right there is why there are so many more plants in the world than there are top predators. There's just not enough energy to go around at the top.
And this is an absolutely critical point. Energy flows. It's a one-way street. It comes in, gets used, and it's gone. But matter, the actual stuff, the building blocks of life, like carbon, nitrogen, water, that stuff gets cycled. It's not lost. It gets reused over and over, thanks to those decomposers. They return it to the stage, ready for the next act.
Okay, so we've seen the stage, we've met the actors. Now for the really cool part. Let's put it all back together and watch how they actually interact. This is the great interplay. You see, this relationship is a total two-way street. It's not a monologue, it's a dialogue. On one hand, yes, the non-living environment sets the rules. It forces limits on life and says, you can live here, but not there. But, and this is so important, living things actively push back. They change their surroundings, sometimes in really profound ways. And this process actually has a name. It's called niche construction. I mean, think about beavers. They're the ultimate ecosystem engineers. They don't just find a pond, they make a pond by building a dam. Or what about earthworms? They're quietly down there aerating the soil, changing its chemistry, literally making it a better place to live for themselves and for all the plants around them. And of course, the actors don't just interact with the stage, right? They interact with each other.
And there are all kinds of relationships. You've got mutualism, which is a total win-win, like a bee and a flower. You've got predation, a clear win-lose. But check out that last one, amensalism. This one's kind of weird. It's a lose-neutral situation. So one organism is harmed, but the other one gets nothing out of it, positive or negative. A great example is a huge tree that casts a shadow and kills the little plants underneath. The tree doesn't care one way or the other, but the small plants definitely lose it.
So if the environment is setting all these limits, what are the actual rules of the game? Well, let's look at two fundamental laws that really dictate the boundaries of where life can exist. Okay, so on one side, you have Liebig's law of the minimum. The bottom line here is that your growth is controlled by your scarcest resource. It's all about what you have the least of. Then, on the other side, you have Shelford's law of tolerance. This is about conditions. It basically says that for anything, temperature, pH, whatever, there's a just right Goldilocks zone. Too much or too little, and things get really stressful or even impossible. And here's how they connect, and it's so important. You know that saying, a chain is only as strong as its weakest link? Well, that's ecology in a nutshell. An organism's survival isn't about all the things it has plenty of. It's all about that one single thing that's in shortest supply. That one weak link can bring the whole operation to a grinding halt.
This chart just shows Liebig's law perfectly. So look at this poor plant. You can pump it full of phosphorus and potassium, give it tons of this stuff, but it doesn't matter. Because its nitrogen is low, its growth is totally stunted. That one scarce nutrient is a bottleneck, and it's holding everything else back.
And we really can't forget just how powerful this idea of environment modification can be. I mean, we're not just talking about beavers in a river. Let's go back, way back. Billions of years ago, these tiny little organisms called cyanobacteria started pumping out oxygen as a waste product. And they did it on such an unbelievable scale that they literally changed the entire chemistry of Earth's atmosphere. They made the air breathable and paved the way for, well, for us, and all the complex life we see today. It's incredible.
And that brings us to a huge final thought. We've seen how organisms can shape their world, from a single beaver pond to the very air we breathe. So it really forces us to ask a tough question, right? What happens when one species, us, becomes the single most powerful force of niche construction on the entire planet? What does it mean for the future of the global ecosystem when we are the limiting factor for so many other species out there?